So that's like the theorem. So what the definition of a Cauchy sequence is, the terms of the sequence get close to each other. And how close? Well, like as close as you want, right? So that informal thing, we kind of know how to translate that to a formal expression. How close? No matter how close we want. So the definition of Cauchy had better start with A for all epsilon bigger than 0. And the terms of the sequence get close together. So that should mean the difference between terms of the sequence gets really small. And that's just a matter of figuring out what goes between. So for what types of numbers m and n is that difference very small? Is it for absolutely every m and n? It should be for like really big m and n values, right? So just like the definition of a limit, what should go in between those? So in order to remember that definition, the formal definition, we have a definition that looks an awful lot like it. What does it mean to say that a sequence converges to A? It means that as the parameter n gets big, the terms of the sequence get really, really close to A. Now give me the definition of the limit. AN converges to A means
epsilon greater than 0 there exists a big N such that little n is greater than big N. And then the absolute value of is it AN minus
the limit is called A right now.
A?
Yeah.
Is less than epsilon.
Yeah. I'll put that symbol there too. So a sequence converges to A if no matter how small you want the difference between the terms to be, you can get them that small by letting n be big enough. A sequence is Cauchy if no matter how close you want the terms of the sequence to be to each other, they are eventually that close to each other, as long as m and n are big. So you should think of a sequence being Cauchy as saying that the terms of the sequence think that they're getting close to something, but you don't know what they're getting close to. Because they're all getting close to each other, so there should be something they're getting close to. The theorem we proved last time, the Cauchy convergence theorem, what does it say? Well, you kind of told me like a moment ago informally. The Cauchy criteria, the Cauchy convergence theorem says that if the terms of the sequence get really close to each other, then there's a number that they're getting close to. So let's just make that more formal. So the Cauchy criterion says AN is Cauchy if and only if What was the big theorem we proved on Friday? Yep. So, putting that down, I guess I should have the definition of Cauchy here. The Cauchy criterion for convergence says that a sequence is Cauchy if and only if it's convergent. It doesn't tell you what the limit is, but the limit exists if and only if the sequence satisfies this Cauchy criterion. Cool. So, here's what I'm going to do today. I'm going to extract, well, group walk. So you are going to extract from the definition of Cauchy a weaker condition that's easier to check that will imply convergence. Definition. AN is contractive if there exists some big C in between 0 and 1, such that for all M and N, for all N, absolute value AN plus 2 minus AN plus 1 is less than or equal to constant C times AN plus 1 minus AN. So, what does that say? A sequence is contractive if there's a number C between 0 and 1, so something smaller than 1 and positive, which satisfies that when you take the difference between two consecutive terms, that difference is less than or equal to that constant times the difference between the two previous consecutive terms. And here's the theorem for today. Proposition. If AN is contractive, then AN is convergent. The converse isn't true. There are convergent sequences that are not contractive, but contractive is a condition that's reasonably easy to test for. And so today's a group work day. So today's homework is in fact going to be you turning in a completed version of the notes for the day. And I'm going to have us go through it in a particular order just to get an idea for the spirit of it. So we'll close by thinking about the proof of this proposition. Why should contractive imply convergent? I'm going to search. On the next page, let's use this idea to show that a sequence converges. Here's a sequence. Let's consider the sequence whose first term is 1, whose second term is 2, and whose every term after that is the sum of the previous 2, but then you divide by 2. So, I don't know, it's something that looks vaguely Fibonacci-ish, but instead of taking the sum of the previous 2 terms, you take the average. I claim that this sucker converges. I don't know where it converges. That's not the point. I claim that it's convergent. And here's how I think we'll go about doing it. Let's start by proving that this sucker is contractive with a constant of 1/2. So let's write down a good strong want to show off in the margins. If I want to show this thing is contractive with a constant of 1/2, look at the definition of contractive. What do you need to prove? I guess on the board I don't say the notation of what it means to have a contractive constant of 1/2. It means that the C is 1/2. The C is a contractive constant. So, tell me what you need to prove. Looks like on the board, right? So, tell me what you need to prove.
That C is 1/2 for xn, and it's contractive.
Yeah, I want to show that this sequence satisfies this condition with c equal to 1/2. So I want to show that this stuff happens with c equals 1/2. So we want to show that for every natural number n, the absolute value of xn plus 1, xn plus 2, minus xn plus 1 is less than or equal to 1/2 absolute value xn plus 1 minus xn. That seem fair enough? So that's, maybe you can tell from here the reason that this condition of contractiveness is useful when thinking about row occurrence relations. Let's use this idea of this row occurrence relation on this. So by using the occurrence relation, how could you rewrite absolute value xn plus 2 minus xn plus 1 in absolute value? Do I have something I could just replace one of those two things by? Yeah, the occurrence relation says xn plus 2 is equal to a thing. You don't lose any information when you replace something with something it's equal to, and maybe you'll get something useful out of it. So replace it with this thing that it's equal to. What do you get?
Are we keeping the xn plus 1?
Would you like to? I mean, you could replace this with n plus 1, so everything else would be down by 1. But let's think about what we want. I want xn plus 1 and xn to show up. So, would you want to also replace xn minus xn plus 1 with the previous two terms? It wouldn't be wrong to, but I think I don't want to. And you know what? If we do this and it doesn't work out, we can do that as a follow-up. Not everything works the first time you try it. Keep that second idea in your back pocket as something else you could hit this with. So, you use the occurrence relation on xn plus 2. What do you get?
Xn plus xn plus 1 over 2 minus xn plus 1.
And hopefully this simplifies and cancels down or something in a nice way. Simplify that down as much as possible with the idea that you want to get something that looks like this showing up. Take it and simplify it. What do you get?
Xn over 2 minus xn plus 1 over 2.
Nice. And I guess absolute value bears around everything, because you haven't done anything to get rid of them. Keeping in mind the goal, the want to show. Do you have any follow-up observations?
You can pull 1/2 out.
You can pull the half out. In fact, there's a rule that says you can pull it all the way out of the absolute value, right? Yeah. And at this point, you don't need to cite the precise property of absolute value you're using. So what do you get when you do that?
1/2 x minus xn plus 1.
Oh, cool. Is that what you wanted to show up there?
It's close.
Yeah, it's just off by the things are in the wrong order, but does that matter? Yeah, okay. So depending on how picky you even want to be to have the exact form matchup, maybe there's another step that you reverse the order on subtraction. All right, so that means that this sequence is contractive with a contractive constant of c equal to 1/2. So, according to the theorem that's not written on the board, but the proposition that you will prove soon, what does that let you conclude? Oh, so neat. Does this have a limit? Groovy. So, there's the idea of this statement of contractiveness. It gives you a strong, a reasonably easy to check condition that will imply a sequence converges. I don't know. Let's hit this sequence with let's see if monotone can. Well, no, let's not get too distracted. This sequence isn't monotone. Right. It goes from 1 to 2 to the average between 1 and 2, which is 1.5. So it increases and then decreases. It's not monotone. Can't use monotone convergence. But it is contractive. So here's what the rest of this packet contains. Well, if contractive implies convergent, then you better be able to prove that. And you have a plan that does that. We know that Cauchy is equivalent to contractive. And certainly just knowing it's contractive doesn't tell you what the limit is, so you're not going to be able to come up with a guess for the limit. So the Cauchy criteria is that I want to use. So that means at some point we want to figure out the difference between AN and AN and exit value, because that's what is in the Cauchy criteria. So the first bunch of this proposition is analyzing that difference, calling it into something that looks like a geometric sum, and using that to bound the difference. So there's step one. The other thing I'm going to have you do is another example an awful lot like what we just did, which will hand you a sequence which converges because it's contractive. So you'll know it has a limit. You can then use the fact that it has a limit to prove that the limit has to be the square root of 2. All right, so at this point, it's group walk time. So, start at the start. Let AN be a contractive sequence. You want to prove that AN is convergent.
just,
This looks like some people are feeling stuck on the box one. This comment there that says to use induction. What do you need to do to use induction to prove a claim like this?
Usually show it's true for the n plus one case.
show it's true for at least one case. Assume it's true for all of those cases, and then add one and see if it's still true.
Yeah, so you can show it's true for the smallest number k for which the statement makes sense. So I don't know, maybe k equals 1 is the smallest k for which it makes sense? Is the claim like pretty obvious when k equals 1? It often is. That's not always the case. There are some inductive proofs where like the hard case is the base case and the inductive step is automatic. So do the base case. Next, do the inductive step. So, what do you do to do the inductive step of an inductive argument?
K plus 1.
Is what you need. So you need to prove the thing is true for the next k, assuming it's true for some fixed k. So, fix some k. Assume the thing you want to show is true for that k. And let's include a nice strong want to show. You now want to show that it's true for the next k. So now ratchet up all those k's by 1. K plus 1 is k plus 2 minus k plus 1 is less than or equal to k plus 1 minus 1. And maybe I'll put pink parentheses around there. So I really want your inductive step to have a strong statement of what the inductive assumption is. between 0 and 1 and square it. It's still between 0 and 1, right? They expect to get smaller. This looks an awful lot like the thing that's in the definition. Right? So that is it's close to it, but not quite. Contractive says that this is compared to the form of the usable form. So this Bostock is saying that instead of comparing to the form of the involved in Boston. Yeah, so let's see what you can do. So let's see. In the inductive step, you're like at a stage. Where you see some like absolute value AK plus 2 minus AK plus 1, alright? You want to show that's less than or equal to some stuff. So anything you see that has AK plus 2 minus AK is less than or equal to is something that would be like not unreasonable to mess around with. And what do you know right now? You know the inductive assumption, and you know that the sequence is contractive. What does contractiveness tell you about this?
It is the C value A, K plus 1 minus A.
Cool. Do you know anything about that?
We can relate it to what we have on the paper from induction if we have A1.
It doesn't that have to be less than or equal to CK if A2
Yeah, say that. So what does the inductive assumption get you now?
The inductive assumption gives us that is now less than C or K. A2 minus A1.
Yeah, so leave this C alone. And the pink tom looks like that, right? So what does it, use the inductive assumption, what does that give you? the idea to chase on step 2. So we know a bunch of stuff about contractive sequences as long as you subtract consecutive terms. And all that step 2 does is it says instead of taking the difference between two non-consecutive terms, just take a bunch of differences between consecutive terms and add them up. And maybe the right way to motivate this might be as follows. Let's think about what this means for like A4 minus A1. It says that that should be less than or equal to absolute value. So this is from K, starting at 1 and going up to 4. So if I just asked you to justify why that is true, what would you say?
Not super formally, just each individual.
Well, look on the side with like the 3 different absolute values. What would happen if you just lost all the absolute values?
You would have a telescoping sequence.
Telescope. So if you could like collapse everything inside of a single set of absolute values, yeah. If there weren't any absolute values, then yeah.
So should we use reverse triangle inequality like that?
Yeah, let's try the triangle inequality. So, according to the triangle inequality, this is bigger than or equal to absolute value A2 minus A1 plus. Oh, cool. Is that like exactly the thing that's on the other side? Oh, cool. Do you think you could do that for any m and n now instead of m equals 4, n equals 1?
100%.
Cool, do that. And in fact, given that we have 10 minutes left, I wouldn't worry about sketching out a totally formal argument. Write down enough that you could then turn it into a formal argument on your own time. just try to make some summary statements of how the rest of this will go. So all of step 2 is like use the triangle inequality a bunch of times. And like depending on how formal you want to be, you can use induction if you really don't like having dots in your argument. That's fine. But I'm also happy with like summation notation showing up. We have an n-tom triangle inequality. So let's see what we have so far. We have absolute value am minus an is less than or equal to a sum of absolute value ak plus 1 minus ak's. I'm not going to put the bounds on that sum because I'll get them wrong. They're on the previous page. What do we know about absolute value ak minus ak plus 1? By step 1. It's like c to the k minus 1 times some stuff. Where the very parameter in the sum is k. What type of sum is that? Geometric? We have a formula for geometric sum, or a formula for the geometric series. Keep in mind that this series isn't starting at 1. It's starting at k equals like m plus 1 or n plus 1 or something. So if you can convince yourself that that geometric series gets really, really small as the parameters m and n get really, really big, that should make you very happy. Because then you can say, aha, since this thing converges to 0, no matter how small an epsilon I pick, because eventually I need to have a full half epsilon show up because of the definition of Cauchy. There exists a big N that'll come from the geometric series, such that for all m and n bigger than big N, some geometric series terms are less than epsilon. But you know this is less than a geometric series, so it's less than epsilon. So there's just wrapping up the details. You have to now put those into wads. What do you think? Does that seem like something you can do? Does it feel like you have the spirit of it? Cool. So finish up those details. The homework for today is exactly completing this group walk. And after you've done all that, this thing that we did all together is part of the group walk too. It should be like 3 points on this particular homework. And then play the same game as we played here with a different sequence. Show that this sequence is contractive. I think I even suggest what the contractive constant will be. It doesn't matter though what the contractive constant is, as long as it's in between 0 and 1 strictly. I guess a bigger contractive constant will result in slower convergence, but that doesn't matter. The limit will still exist. Cool. So, I just wanted to make sure to get that summary before time is just up. So I'm going to be quiet for a bit. The room is yours. We've got a few minutes left to keep on talking.